Hi there and welcome to our rock bolt demonstration video. This video was prepared by Master of Engineering graduate students Matt Davidson,
Abdullah Siddiq,
and Paul Weingartshofer
as a course requirement for Civil 6002 mine excavations at Dalhousie University. In this video, we are going to perform a laboratory experiment that simulates how rock bolts can be used to stabilize a jointed rock mass. The experiment is based on a rock bolt model shown in Practical Rock Engineering by Everett Hook, which is based on an experiment by Tom Lang. The experiment will consist of filling an elevated box full of crushed rock to simulate a jointed rock mass, tensioning a number of rock bolts through the crushed rock, and removing the bottom of the box to see if the crushed rock remains suspended or stabilized by the rock bolts.
Background. Rock bolts are commonly used in the civil and mining industries to stabilize the walls and ceilings of tunnels. In order to apply a rock bolt, a hole is first drilled into the rock, then a rock bolt is inserted and grouted into place. Once the grout has been set, the rock bolt is tensioned. This figure, as shown in the Practical Rock Engineering book by Hook, shows the basic principle on how rock bolts work. When the rock bolt is tensioned through a jointed rock mass, the compressive forces that the bolt exerts on the rock mass causes increased shear resistance along the block-on-block interfaces. In terms of rock bolt model, the compression forces from the rock bolts cause increased particle interlocking and subsequent increased shear strength. Compression arches form between each rock bolt.
Design. Our rock bolt model is primarily constructed out of wood. The internal dimensions of the box are approximately 3 feet by 3 feet and the box stands about 3 feet high. 2x12s were used to construct the box and 2x4s were used to construct the box legs. 1.5 inch angle steel was used to create a lip around the inside of the box to help support the crushed rock, and around the outside of the box to allow us to clamp on the box base plate. The box base plate was cut out of 3/4 inch plywood and holes were drilled in a set grid pattern to allow us to place the rock bolts. Our miniature rock bolts are approximately 12 inches long and cut out of 1/4 inch threaded steel rod. 1.5 inch washers were attached to the ends of the rods as shown. After some trials, the washer sizes were increased to 2 inch diameter. 1 inch clamps were used to attach the base plate to the angle steel. The crushed stone used consisted of 1 to 2 inch clean gravel that was generously donated by a local quarry.
Procedure. As described by Hook, the rock bolt model should provide effective reinforcement to the rock mass when the rock bolt spacing is less than 3 times the average rock diameter. We wanted to test this claim and decided to conduct several trials where the bolt spacing was varied from 8 inches to 6 inches, 5 inches, and finally 4 inches. Assuming an average rock diameter of about 1.5 inches, this means that our trials range from about 5.5 times the average rock diameter down to about 2.5 times the average rock diameter. The procedure for filling the box and removing the base plate is as follows. 1. Attach the base plate to the box using clamps. 2. Place the rock bolts into the selected grid spacing pattern. 3. Begin filling the box with gravel, being sure to manually level out and maneuver the gravel in order to ensure tight particle interlocking. 4. Compact the gravel in 3 to 4 inch lifts using hammers or spare 2x4s, and use a spray bottle to dampen the gravel in order to keep dust down. 5. Place the final lift of gravel so that the entire rock mass is about 10 inches thick. 6. Attach the top washers and tension the nuts until the washers begin to bend slightly. 7. Begin removing the clamps that hold the base plate to the box and ensure that everyone has their feet clear, is using proper lifting techniques, and is using effective communication to coordinate the removal of the base plate.
Trial 1. Trial 1 consisted of 8 inch bolt spacing. This spacing required 16 bolts. We loaded the box with gravel, tensioned the rock bolts, and removed the base plate. As you can see, this trial failed the moment we began to remove the base plate. Causes of failure likely included too much width of bolt spacing, not compacting the rock well enough, not providing enough tension to the rock bolts, and not placing the bolts close enough to the perimeter of the box.
Trial 2. Trial 2 consisted of 6-inch bolt spacing. This spacing required 25 bolts. Once again, we loaded the box with gravel, tensioned the rock bolts, and removed the base plate. As you can see, this trial failed the moment we began to remove the base plate. However, we could feel more support provided by the bolts than in trial 1, prior to letting go of the base plate. This indicated that the rock bolts were providing some assistance. Causes of failure likely included too wide of bolt spacing, not providing enough tension on the rock bolts, not placing the bolts close enough to the perimeter of the box, and too small of washer size.
Trial 3. Trial 3 consisted of 5-inch bolt spacing. This spacing required 49 bolts. Let's see if this trial was successful. As you can see, this trial began to fail in the center as we removed the base plate. However, the rock mass appeared to be somewhat supported around the perimeter of the box prior to total collapse. Causes of failure likely included too wide of bolt spacing and too small of washer size.
Trial 4. Trial 4 consisted of 4-inch bolt spacing. This spacing required 64 bolts. This was also the first trial where we used 2-inch washers instead of the 1.5-inch washers. We loaded up the box with gravel and provided more than enough compaction between lifts, tensioned and retensioned all the rock bolts, and removed the base plate. As you can see, this was our first trial to be successfully supported by the rock bolts. The success of this trial was likely due to the close bolt spacing. This confirms the statement made by Hooke that the rock bolts should provide effective reinforcements to the rock mass if the bolt spacing is less than 3 times the average rock diameter. Also, the larger washer size was likely a contributing factor. A photo of the underside of the rock mass clearly shows the compression arches and demonstrates how rock that is not contained within the compression zones will fall out of the rock mass. A load of approximately 50 pounds was placed on top of the rock mass without causing failure. We decided to induce failure by tapping the board on the side of the box to cause more and more rocks to fall out of the rock mass. Once the compression zone around one of the bolts was compromised, the entire system collapsed. Let's see that again in slow motion.
Trial 5. Trial 5 consisted of 4-inch bolt spacing and 64 bolts. With the success of Trial 4, we decided to repeat the trial with the addition of a mesh across the bottom of the rock mass. The purpose of the mesh was to contain rocks that would otherwise fall out of the bottom of the rock mass if they were not held within the compression zone as seen in Trial 4. After performing the routine of filling the box with gravel and tensioning the bolts, we removed the base plate. The rock mass did not appear to move whatsoever, and any loose rocks were contained by the mesh. Although this test was a bit boring, it was nice to not have to clean up all the gravel for once. The success of this trial was again due to the close bolt spacing and larger washer size. The addition of the mesh helped to keep the entire rock mass supported and contained. A photo of the underside of the box shows a nice, clean, supported rock face.
Conclusion. This video demonstrated how rock bolts can be used to support a rock mass using a rock bolt model that we constructed. Several trials were conducted where the rock bolt spacing was varied from 8 inches to 6 inches, 5 inches, and finally 4 inches. Trials where the rock bolt spacing was greater than 3 times the average rock diameter resulted in failure. Trials where the rock bolt spacing was less than 3 times the average rock diameter remained stable. Rock bolts provide support to a jointed rock mass by creating a compression zone and arching effect between the bolts that prevents the rock mass from collapsing. A steel mesh can be added to the face of the rock mass to prevent falling of loose rocks. Although not specifically addressed earlier in this video, it should be noted that the thickness of the rock mass can also have an effect on the stability of each trial. As described by Hooke in Practical Rock Engineering, the rock bolt length should be approximately 2 times the rock bolt spacing. Applying this clause ensures that there is adequate thickness of the compression zone between each rock bolt. If we consider our trials where we used a fixed rock mass thickness of 10 inches and assume a stress distribution that extends outward from each rock bolt at about a 45-degree angle, this means that the thickness of the compression zone ranged from approximately 2 inches in trial 1 with the 8-inch rock bolt spacing to 4 inches in trial 2 with a 6-inch rock bolt spacing, 5 inches in trial 3 with the 5-inch rock bolt spacing, and finally 6 inches in trial 4 with the 4-inch rock bolt spacing. As shown, only trials 3 and 4 had rock bolt lengths greater than or equal to 2 times the rock bolt spacing. This was likely also a contributing factor to the instability of trials 1, 2, and 3. This concludes our video. We hope we helped you gain a new understanding of rock bolts and provided you with enough information to attempt this experiment on your own. This demonstration was based on the rock bolt model as shown in Practical Rock Engineering by Everett Hooke, which is available for download at www.rockscience.com.